move on to amino acid compound specific isotope analyses. What I'm going to do is go over sort of why different amino acid nitrogen isotopic compositions change with a trophic transfer and how that can be used. I'll give you a few examples in the modern ocean of what we can use this information for. The motivation for the work is, to understand why there are changes in nitrogen isotopic composition of organisms with a trophic transfer. And one of the other motivation is that measuring the nitrogen isotopic composition of amino acids allows us to normalize for baseline changes. And I'll explain that. Okay, so here's a simple food web. It's one of my favorite food webs because it results in sashimi. All right, so we have an organism that's taking up nitrogen here. It gets grazed upon by some flying fish, and the rate of loss of 15N ammonia, so through excretion, is greater than the rate of 15N ammonia excretion, and by mass balance, it results in an enrichment in the biomass of the consumer. It happens at different trophic levels, so by the time you get to sashimi, the isotopic composition is, the nitrogen isotopic composition is high. Okay, so we can parameterize that. The delta 15N value of a predator is equal to the delta 15N value of the prey by plus some enrichment factor here. It's widely held that it's around 3 per mil per trophic level, but it varies. Okay, so ideally what we'd like to do is be able to measure the nitrogen isotopic composition of various organisms and put together a food web. All right, cool. That's a fairly easy measurement to make. The problem is that, these things are not only fixing nitrate, but they're fixing ammonium, they're fixing N2. So the baseline, the isotopic composition of the base of the food web can vary depending on the proportions of utilization of these different forms of nitrogen. If you do that, if it's all nitrogen fixation, that's going to be propagated through that food web into our sashimi. And the nitrogen, it will affect the nitrogen isotopic composition. Diagrammatically, it looks like this. We have a sort of our classic food web where production is being supplied, or the nutrients for production are being supplied through flux across the picnic line. Nitrate comes in, it's being fixed, there's some fractionation, there's some recycling, and then these phytoplankton get eaten by a grazer. The grazer gets eaten by a consumer here, something at maybe trophic level 3. There's a constant shift there. So we have our food web. But if that food web is influenced by nitrogen fixation, we could have the identical consumers here. There's the same shift, but we've added some nitrogen to that. Nitrogen fixation, which lowers that overall delta 15N value here. So this organism, despite being a grazer at trophic level 2, will have a delta 15N value that's substantially different from this. If you were to just study the food web based on the delta 15N value of the consumers here, despite them being the same, you might interpret that they're different because they have different nitrogen isotopic compositions. The situation is worse in regions where there's denitrification because nitrate is fluxing up here at values of plus 10 per mil, so this whole food web is shifted out here off the screen. So it's really, really important to nail down what the isotopic composition of production is that's feeding each of these food webs. Okay, so how do you do that? Okay, this is an example of myctophids. These are lanternfish. These are little tiny fish, bait fish, I guess, I don't know, micronectin. They have a weird lifestyle there. They vertically migrate through the ocean. In the daytime, they swim down to avoid predation, and they live at around 400 meters. At night, they come up to the surface and they feed, and at daytime, they go swim back down. Again, they feed at the surface because that's where production is. All right. So there was a study of these that looked at McTophid delta 15N values from a variety of regions. Here, the Tasman Sea, the California Current, the Gulf of Mexico, North Pacific, the Mid-Atlantic, and the delta 15N value range 6 to, 12 per mil roughly. At 3 per mil per trophic level, that's 2 trophic levels. All right, it's thought that these things feed on zooplankton. Well, if this isotopic value is indicative of zooplanktivore, if this is 2 trophic levels above that, these are carnivores. These are top carnivores. This is a trophic level of a tuna. I mean, if these were carnivores at 100 millimeters in length, we wouldn't want to stick our pinkies into the ocean because these things would ravage them. They'd eat us. So it's quite unlikely that this linear relationship or quasi-linear relationship is due to a change in trophic level. But how do we prove that? How do we establish what the isotopic composition of the base of the food web for something that vertically migrates 400 meters in the ocean? It's really difficult. You could collect samples at depth, you could collect samples at the surface, but I mean, they're eating mainly at the surface, but I doubt that they stop eating when they migrate in the summer or the daytime down to 400 meters. Well, one way in which we can do this is to measure the nitrogen isotopic composition of individual amino acids. And this is a really nice paper published now over a decade ago by Jim McClelland and Joe Montoya. And what they did is they simply looked at the difference between a grazer and its algal source. So this grazer was fed in culture, a monoculture of algae. So the isotopic composition of both of these are measured. So here's the bulk. There's an enrichment here. This is the difference between consumer and food. There's an enrichment around 2 per mil, close enough to 3 per mil. That's the whole tissue. But this enrichment is a combination of some amino acids that change, sometimes by quite a lot. Glutamic acid here is enriched by 7 per mil relative in the consumer relative to the producer. There are other amino acids that don't change at all. And it's not only during the first trophic transfer, but by subsequent trophic transfers. The difference between glutamic acid and phenylalanine in an organism that's trophic level 4 like a tuna is up to 30 per mil. It's because the nitrogen isotopic composition of this group of amino acids changes very little, but this changes a lot with each trophic transfer. And we're looking at a mass balance in the isotopic composition of the protein from some amino acids that change a lot, some that don't change much at all. So we've called these, for better or for worse, the trophic amino acids because they change with trophic transfer. The others are called source amino acids because they record the delta 15N value of the source of those amino acids at the base of the food web. Okay, so let's look at these McTophids, the lanternfish. And we're going to look at the trophic position calculated from the difference between the isotopic composition of glutamic acid and phenylalanine divided by this trophic transfer coefficient. All right, so simple equation, trophic position, what we see is that by and large, there's no difference in those. They're at the same trophic level, so that 6 per mil variation that we saw from one region to another was driven entirely by the biogeochemical cycling of nitrogen at the base of the food web. And you know now that can change a lot across the ocean. Well, this is a way in a consumer that we can control for that, and we can learn something about the trophic ecology of these organisms. Now, it's probably more complicated. The mechanism driving these variations is probably more complicated than what's shown in this diagram. But we can think of a trophic amino acid like glutamic acid. Glutamic acid undergoes deamination, and there's an amine group on there that contains 14N and 15N. Which of those is the weaker bond? 14N. Which of those when you break that carbon-nitrogen bond there is going to preferentially break? 14N. So yes, we lose 14N, and the glutamic acid becomes enriched in 15N as it's converted to an alpha-glutaric acid. Something like a source amino acid like phenylalanine, it undergoes hydroxylation to tyrosine. That's the main pathway. There's some degradation pathways that break this nitrogen-carbon bond, but they're not quite as important as this pathway, and there's no primary isotope effect associated with hydroxylation. So we would expect constancy in its isotopic composition with trophic transfer. So there is no equivalent of alpha-glutaric acid. So it doesn't undergo an exchange of its exchange of its amino nitrogen very much in an organism. This is probably oversimplified in terms of the mechanisms controlling the difference in isotopic composition of trophic and source amino acids. It probably has more to do with the metabolic activity of these compounds versus the trophic versus source amino compounds. But on a first approximation, this is a reasonable explanation that explains our observations. Okay, so diagrammatically, this is what we would anticipate. There is a difference between source and trophic amino acids in algae, and that should be accounted for. But with each trophic transfer, there's a small change in the isotopic composition of source amino acid like phenylalanine, but it's not nearly as much as a trophic amino acid. Here, this is around 8 per mil per trophic level. Here, it's around 0.4 plus or minus 5, effectively 0. So with each trophic transfer, there's an enrichment, 7.5 per mil per trophic level. So the difference here is 7.5. Here, it's double that, about 15 per mil at trophic level 3. These are big numbers. These are big changes that we see. We can calculate trophic transfer. This is work of Yoshito Chikarishi. He suggested using glutamic acid, or they suggested using glutamic acid and phenylalanine. They show the most consistent relationships in at least marine plankton and macroalgae, the difference between glutamic acid and phenylalanine, this value here, which is known as a beta value. And it had the largest magnitude change. So any variation in this trophic enrichment factor, the calculated trophic position, because it is so large, is going to be less sensitive to that variation. Importantly, a good lab is going to make multiple measurements of the isotopic composition of glutamic acid and phenylalanine. So you do multiple measurements, you get an uncertainty. This is a number in which has been measured in a number of different macroalgae, and we have an uncertainty for that, and we have an uncertainty in this. You can propagate those errors to come up with a reasonable conservative estimate of trophic position. Okay, the advantages. Well, the relative trophic position is estimated based on 2 or more. Doesn't matter. You can use more than just glutamic acid and phenylalanine, isotopic composition from a single consumer. And guess what? That consumer is doing a much better job at integrating the base of the food web than we could ever do. We can collect samples, but we don't know if those are the samples that are based on the food web that these organisms are eating. But by measuring the isotopic composition of a source amino acid, that's going to be indicative of the base of the food web that these organisms are feeding on. Okay, this is a little bit of a spoiler alert for those who are dealing with both terrestrial and marine systems, but it's by no means a showstopper. The difference between the isotopic composition of glutamic acid and phenylalanine is very different in terrestrial C3 plants than aquatic. Here, this is at 3.4 per mil, the diagram we saw. But in terrestrial plants, glutamic acid is depleted relative to phenylalanine by 8.5 per mil instead of enriched by 3.5 per mil. So that's 11 per mil different. You know something? That's something we can really use to our advantage too. You have to be cognizant of it. These things start at different places. So at trophic level 1, the isotopic composition of phenylalanine and glutamic acid are going to be the same. But in an aquatic system, glutamic acid will be enriched relative to phenylalanine by about 7-8 per mil. Now this happened had a postdoc. She was actually a student in IsoCamp. She wanted to analyze the isotopic composition of turtles in the Caribbean. And I sort of said, well, I think we kind of know what the answer is. They eat something called turtle grass, right? They're grazers. Yeah, but their isotopic composition varies. Yes, the isotopic composition of nitrogen in turtle grass varies with region. And I said, all right, well, go ahead. Analyze the samples. We got the money, you got the time, do it. She sheepishly came into my office one day and said, Brian, I've got some problems with the trophic position calculation of those green turtles from the Caribbean. Their trophic position is low. I'm like, how low? Well, they're 1. What do you mean they're 1? It can't be 1. Okay, let's think about this. Hey, turtle grass. Isn't turtle grass evolved from a terrestrial grass? It turns out that, yeah, in turtle grass, glutamic acid is depleted by 8.5 per mil relative to phenylalanine. So when we changed the beta value in here, calculated the trophic position of those green turtles, using this value instead of this value, the trophic position came out as 2. Okay, so here's another example. Another student from IsoCamp came to my lab and wanted to analyze ancient humans from Rapa Nui. Long story, she was Norwegian. She grew up in Oslo near the Kon-Tiki Museum. This was the Heyerdahl Museum, and there were lots of samples from Easter Island because he was the one that built this balsa wood raft and sailed it from South America at Easter Island to show that, you know, it could be settled by South Americans. And so this kid grew up with, you know, this national hero who had studied Easter Island. She was an anthropologist, and she wanted archaeologists, and she said, I want to do something that reminds me of home. So she came to my lab as an RIR student and said, I want to look at the diet of the early humans on Easter Island. Because a paper had come out said that they don't eat fish, that they prefer their protein from rats and chickens and terrestrial crops that they grow. So we analyzed the isotopic composition of amino acids in humans, rats, chickens, and marine fish. And we calculated the trophic positions. First, using a fully terrestrial diet, and again, using a fully marine diet. And the only difference between these two equations is this number here. And again, they're different by 11 per mil. That's a huge difference. Did they eat a fully marine diet? Well, this is the range in human trophic level. There's a nice paper that looked at millions of records of food supply for nations. And it turns out the average trophic position of a modern human is 2.2. And the range is 2 to 2.7. 2.7 was sort of Icelanders circa 1960. Their trophic position actually has dropped to around 2.6 since around 2000, probably through globalization of the food supply. The Icelanders were probably eating lots of fish and lots of lamb and not many vegetables until sort of there was a greater distribution. So, all right, so that's the range of human trophic level. That's the average. A fully terrestrial diet exceeds that. That's probably unlikely. This is definitely unlikely. But for the marine fish, it nailed their trophic level. We would expect a marine carnivore to be around 3, herbivore to be around 2. So, you know what? We're isotope chemists. We can do an isotope mass balance. We can take a fraction of our terrestrial beta value and a fraction of a marine beta value and calculate a trophic position. Or, in this case, we can make the assumption that the trophic level of the early Easter Islanders was about that of modern humans. And, you know, when you look at the trophic level of people living in Oceania today, it's around 2.2. So you can rearrange this and solve for the fraction of marine organic matter, assuming a trophic level of 2, and it's about a 50-50 mix. If you put that into the equation for humans, you get an overlap value here. So this is an example where we're taking this huge difference in the beta values at the base of the food web between a terrestrial and marine system and using it to our advantage to learn something about what these early humans ate. They ate fish. Okay, so how do we do this analysis? Well, you got to take that protein and break it down into amino acids. You do that using hydrolysis. You boil it in 6 normal HCl for about an hour, 150 degrees. You clean it up, and then there's a 2-step derivatization. The technique is cookbook. It's easy, but it's really tedious because you've got to evaporate strong acids and strong bases. It takes about 3 days to prepare 9 samples. But it's worth it. You eventually get the isotopic composition of many different individual amino acids. This is a chromatograph of amino acids. This is on a GCMS, but it just shows you that there's good separation, well enough separated that we can measure the isotopic composition. It doesn't take too much tissue. The analysis time for each injection is, once you have it prepared, is about an hour. And you get the isotopic composition of about 15 amino acids. If you start off with 5 milligrams of tissue, you inject 1 out of 100 microliters of a solvent to make those analyses. Our accuracy is not quite what we would get for bulk material, but the ranges are huge, so we don't need a high accuracy and precision for this method. And again, we know what the errors are. We can measure those errors and we can propagate them.